Okay, hello everybody, and welcome to workshop number 4 in our Physics 2A series. Today we're going to look at some problems involving circular motion. It's going to build on some of the concepts that you've worked on previously with linear motion. We've got a couple of problems, but before we get started, I want to do some preparation. So we've got our worksheet here. I'm going to copy that over into OneNote, then we can work on it from there. So preparation part 1, let's take a look at that. Okay, grab that for you guys. So it says, begin by reviewing the quantities of interest in linear motion, then write down or work with your teacher to develop the relevant analogs for circular motion. Okay, and this is a big thing for me because when I was first taking my physics course, I got pretty confused on circular motion. And it wasn't until I really solidly connected how analogous it is to linear motion and what particularly are the analogs and where does it differ. When I got solid on that, the problems became very easy. So let's take a look at that. It says part A, how do we represent displacement? What about in circular motion, angular displacement? So if we're talking about regular displacement, you guys have been doing that, right? You think about it as maybe it's like a change in X, or maybe we're doing a different problem and we're going up and down and it's a change in Y, some displacement in the Y direction, some displacement in the X direction. Or maybe if we're just talking about in general, if we don't want to say a specific direction, we could talk about a change in S, where S is position. And a change in S is some displacement, right? Some change in position. Now, what is analogous to this in circular motion? If we do the line here, so when we're talking about linear motion, oh, it's a terrible line. Let's see if we can do a better line here. So this is linear motion. This is the linear motion case. Now, for our analog here, we're talking about circular motion. So it used to be that we were talking about moving along this line. Maybe we move some distance and this is our displacement, right? This is the change in X, if this is the X direction. Now what are we talking about? Now we're talking about this circle going around, or something is going in a circular motion. So we're not just traveling along in one direction, right? If we broke this up with the XY, we would see that sometimes we're traveling in the X direction, sometimes we're traveling in the Y direction. That's a little bit confusing. Sometimes that will be useful, sometimes it won't be. But the core thing that we have, and that the analog for what is the displacement in terms of circular motion, is something called the angular displacement. And specifically what we're interested in, I'll again do a line. We start out with a midline that goes straight through our circle. And what angular displacement is asking is it's saying, if we go from there and we end up at some later point on the circle, say here, then our angular displacement theta asks how many radians, how much of the circle did we turn, or how much angle were we displaced? So this is our analog. This is theta. Theta represents angular displacement. Sometimes you'll see it in degrees. Typically, we'll see it in radians, standard. And then just like if we look at part B here. So this is our analog. So whenever you think of the displacement and circular motion, now you're thinking of an angular displacement theta. So if we answer part A, I'll put A. If we answer part A, then we have some change in position as delta S, and we compare that to some change in angle, some angular displacement theta. Okay. Perfect. So this answers part A. Let's look at part B. So we'll go to the velocity and angular velocity. And we can use the same picture here. Let's see if I can copy my circle down. Okay. So now the velocity is talking about a change, is the derivative of the position over time, right? And the velocity is essentially a speed. It's how much displacement we obtain over some amount of time. We have a velocity. We can ask the same question in regards to circular motion, and then it becomes the same. It's asking, what angle do we turn in what amount of time? So this is asking, what is the change in x per change in time, right? At some instant, say. And this is asking, what is the change in theta per some change in time? And the way that we denote this, right? If we take the limit of this, if we want to find the instantaneous, the velocity at some instant, you know that that is dx dt, the derivative of the position at some instant in time. And then that is equal to v, the velocity. Now we do the same thing here. If we take the limit, the change in the angle, we have d theta dt, and that is going to be equal to what we're going to call omega, which is the angular velocity, omega. So if we go look at part B, we want to put the answer to part B. And what we've got is we started with V, and now the new thing is omega. This is the angular version. We can do a little table. Let's do a table. Can I get a table? Into shape, insert table. Do here. Yeah. Let's put this table off to the side so we can keep track. We're going to want to use these. So this is linear. This is angular equivalent. So on this side we have S is some displacement. On this side we have theta. On this side we have the velocity, and the angular equivalent is omega. Let's see if I can find an omega. There we go, omega. Okay, and then we do the same thing. We talk about the acceleration. Then we can think about the angular acceleration, and just doing the exact same thing. It's thinking about what is the change in our angular velocity in some instant of time. That's the acceleration. So these fundamentally are the analogs. Acceleration and angular acceleration. But that's just the start of it. So we've obtained those. I'm going to erase that. You can pause if you need to take a look at it again, or you can go back. I'm going to clear this out of the way for us because we want some more equations. Oh, I just deleted part of my table. Let's see if we can get, okay. I'll move this over. We're going to go on to part 2. So in part 2, we're going to take a look at the equations that are going to be relevant for most of the circular motion problems that you're going to face right now at this level. Got someone coming into Zoom. 1 second. Okay. All right. So part 2 says, explain the equations below or work to make sense of them with your instructor. So take a look at these, go ahead and pause and think about them and see if you could explain them to me. I won't be able to hear you, unfortunately, but go try to explain them to yourself or explain them out loud, even better. Go through them one by one, see if you can make sense of these. Okay, if you tried that, I'm going to go through them with us now. This, as you can see, is relating these linear and angular quantities, and that makes sense. If we go back to our circle, we're taking a look at this. The linear motion if we just take a look at, let's say our circle is rotating this way, going clockwise here, like this, rotating around. If we at some instant look at the velocity, we look at how something is changing, it seems that it's going to continue to go in this direction. It seems like it's going to be a linear motion. What happens of the circular motion is we continue on in the circle, but we can see the relation between the angular and linear forms, the angular and linear forms. So they're related by the radius. This is the radius of the circle. S, you may remember from your trigonometry, we also call an arc length. We're thinking about how much do you sweep out in a given amount of time as we rotate around. Well, that's dependent on the amount of angle that you sweep out, right? This angle theta. And it depends also on how big R is. If R is larger, then we can sweep out a larger area. We can sweep out a larger area in that same given amount of time. The same thing goes true with V. So you can see that the linear velocity is simply the angular velocity, how much angle we turn in a given time, multiplied by the radius. The radius is like an arm. The radius is like an arm. And the longer this arm is, the more space we sweep out in a given amount of time. And if we're sweeping out more space in a given time, then we're also going faster, right? We're also going faster. Think about the hands on a clock, something like that. If we compare these two different arms, two different lengths, two different radiuses, if they're sweeping out the same angle and the same amount of time, which one of them has a greater velocity at the tip? It's going to be the one with the larger radius. And the same will hold true for the acceleration. The linear acceleration is the radius times the angular acceleration. There's some other quantities that are pretty important before we start to look at these problems, One of the questions that we will ask is about the period and or the frequency. So when we're doing a circular motion, we go in a circle, right? And eventually we get back to where we started. So if this is our start point, we go around and eventually we arrive back at this exact same point. So one interesting thing to look at is what is the time that it takes us to reach that same point? And we call that the period. I told you that we're measuring that angle theta in radians, right? You guys may recall that over the course of a whole circle, there are 2 pi radians. So a circle is 360 degrees or 2 pi radians. So by the time we've gone 2 pi radians, we've reached that full circle. And if we divide that by our angular velocity, we can obtain the period. We know how long it's taking to make one full cycle. How many seconds elapse before we get back to where we were? Alternatively, we could look at the reciprocal of that, 1 over the period, which would be the frequency. And that's asking basically the same question, but in the other way around. It's asking how many times do we cycle per second? How many times do you go around per second? Generally, if you're going around less than 1 time per second, then you want to ask about the period. It's the easiest, makes the most sense. If you're going around more than 1 time per second, then it makes more sense to talk about a frequency. Okay. But those are easily relatable. They're just the reciprocal of each other. You see, you just flip this fraction over here and you get the other one. Finally, a little bit different is the idea of centripetal force. And this was the one that I think confused me some as a student, mainly because I was getting the centripetal acceleration confused with the linear acceleration, and they're not the same. So let's take a look at that. So I talked about the linear acceleration. And if we're looking at that linear acceleration, that's asking at what rate is the change in the angular velocity, I'm sorry, this is the angular acceleration, the change in the angular velocity increasing. So how fast is this circular motion speeding up or changing in speed? So if we imagine a wheel going around, a wheel is going around and around. If the wheel is starting to turn faster and faster, then that's an acceleration, but it's not a centripetal acceleration. A centripetal acceleration is different. What we're talking about with a centripetal acceleration is an acceleration that is center seeking, a center seeking acceleration. A centripetal acceleration looks like this. It's experienced whenever, say, a particle is moving around in a circle. It has some given velocity that's in this direction. This is v. But it's experiencing a centripetal acceleration that changes that velocity. And the effect on the velocity is not to slow it down or to speed it up. You can see these are perpendicular, right? It's not slowing us down or speeding us up, but it's changing our direction. It's changing our direction. And it specifically, it's trying to move us towards the center of the circle. So we move a little ways, we continue on. Our velocity has been redirected. Now it looks kind of like this. Our center-seeking acceleration is still keeping us along the path of that circle, AC. Okay, so those are different things. We have AC. It's V squared over R, or alternatively and equivalently, you can go back to see how these are the same. We have R squared times, R times omega squared. And then you guys remember F equals ma. So if we want to calculate the centripetal force for a given centripetal acceleration, we multiply that centripetal acceleration by the mass. Okay, so these are the tools. I'm going to leave some of these diagrams. Maybe we'll go back to them if we need them. A couple of keys, just these things that are grouped. Make sure you understand what we're talking about when we're talking about it. Now, it used to be there was just an acceleration, right? Or maybe you were doing an acceleration in the x direction, an acceleration in the y direction. Now we've got a couple of different accelerations here. We've got a couple of different quantities. There's angular quantities, there's linear quantities. And in order to solve these problems correctly, we just have to be able to keep them straight. We just have to be able to keep them straight. So make sure that you don't get those confused and study over our diagrams. We've got our linear acceleration, we've got our angular acceleration, and we have our centripetal acceleration. And similarly, we have these linear and angular quantities. And often important in these circular motion problems is the radius. How large is the circle that we're moving along? How large is the circle we're moving along? Okay, so with that, let's go ahead and jump into a couple of the problems. Let's do question number 1. Let's see what they have for us. Okay, this one looks conceptual, which is a good start. So let's see. A particle is moving in a circular path with a steady speed. It has either A, a constant velocity, B, a constant acceleration, C, an acceleration of constant magnitude, or D, an acceleration that varies with time and magnitude. Pause that and think about it. Think about it before I start to go over it. See if you can give us the answer. Okay. So a particle is moving along a circular path. Let's visualize it. Let's visualize it. I'll do the circle once again. And then we're going to put a particle. Particle is just going to be a red dot. The red dot is moving along the path of the circle. So this circle is really just a line representing the path that this particle is going to travel. And it says the particle has a steady speed. A steady speed. So what does that mean, right? It's not saying that it has a constant velocity, right? It's saying something kind of similar, a steady speed. What does this mean in particular, a speed? So speed, as you guys remember, is a scalar quantity, which means it doesn't specify a direction. So we can't say that the particle continues in the same direction constantly, but we can say that its speed does not change. We can say its speed does not change, which is to say that the magnitude of the velocity is some kind of constant, is a constant, it's not changing. So we have some constant velocity, magnitude, some constant magnitude, an unchanging magnitude. Now it may change directions, right? And specifically, we know it will change directions because it's going to trace the path of this circle. So right now it's pointing kind of straight up. Later, if our particle is here along the path, it's going to be pointing tangent along the circle, somewhere off there. It's going to have the same length, it's going to have the same speed, but it's going to be going in a different direction. So these are the little velocity arrows. Okay, so let's go back. We got that picture in mind. Now let's try to look at these different options they give us. Is it going to have a constant velocity? Is it going to have a constant velocity? Well, I think I already said the answer to this. They're not telling us that it has a constant velocity. They're saying it has a steady speed, right? Which are similar but different. If it has a constant velocity, that would tell us the direction doesn't change. So what would this particle do? It wouldn't move in a circle. It would just travel in a straight line. It would just travel in a straight line. That's not what's happening. So this is out. This is not the answer. B, a constant acceleration. A constant acceleration. So this is saying that the acceleration is not changing. That's a little tempting. Let's erase our velocity arrow. Actually, let's leave it in, but let's be sure to mark that this is V at some instant. No, it's a little confusing. Let's erase it. Okay. Remember my picture about how the velocity is changing. We have some constant speed, but this has a constant acceleration. So what would that mean? That would mean there's some kind of acceleration that exhibits a force on this particle. It tries to change its velocity. And we know that it tries to change the velocity in such a way that it makes us move along the path of a circle. So that would tell us that it's pointing us towards the center of the circle, right? If we're pointing towards the center of the circle and we're traveling tangent to the circle, then we're going to start to make a circle. But if this is a constant acceleration, then this direction cannot change, right? They're saying it's a constant acceleration. That's a vector quantity. So what this would do is this would always push us straight to the left, or straight in whatever direction. I've drawn it to the left. But the key here being that it's pushing us straight in some kind of direction. And that would not make us continue to move in a circle. We would deviate from our path, and then eventually, sometime later in the future, we would just change the velocity of the particle and it would just be going straight to the left. Straight to the left. So somehow we need an acceleration that changes directions as we go along the circle. So it can't be a constant acceleration. That's out. Could it be an acceleration of constant magnitude? Okay, so this is tempting because this is already like a parallel to what I was saying about the velocity. The speed is not changing, right? And yet the direction is constantly changing. The direction is constantly changing. So what could create that? Well, we need an acceleration such that our speed does not change, but our direction constantly does change. So we need a centripetal acceleration, an acceleration that always seeks the center with the same magnitude. If it changes magnitude as it goes, and suddenly when we get to this part of the circle, it doubles in magnitude, then we're going to deviate from the circle. All of a sudden, the velocity at this point is going to warp in. It's going to change the shape of our circle. We're not going to trace a circular path. So what we need in order to trace a circle is center-seeking acceleration vectors which are all of the same magnitude. So this appears to be correct. Let's look at D for just to check it out and see why it's probably wrong. But C is correct. Acceleration that varies with time in magnitude. Okay, so this is exactly what I was just saying we don't need. An acceleration that changes in time, changes with time in magnitude. So if at some later time when we're going around the circle, the magnitude changes, it gets bigger or it gets smaller, then we're going to start in a tighter circle. There's going to be more force pushing us towards the center. So we're going to get pushed in towards the center and we'll start to trace a smaller circle. Or if suddenly the acceleration is still center seeking, it still points straight to the center, but it's shrunk, it's now smaller, then we're not going to feel as much force. So our velocity is going to tend to try to carry us in the same direction that it was. And we're going to start to trace a bigger circle. And we're not going to end up making a circle. We're going to end up making some kind of a shape, like if I tried to draw a circle like this, something like that. That's not right either. So the answer is C. The answer is C. Let's look at number 2. Looks like we're going to do some math in this one. Okay. What do they have for us? A wheel is initially at rest. All right. Initially at rest. Its angular velocity increases uniformly and reaches 80 radians per second in 5 seconds. The net angular displacement will be what? Will be what? Okay, good question. So what did they tell us? We got to pick out all the information from here. The wheel is initially at rest. So initially, it's not moving. It's not moving. So that tells us that omega I is equal to 0, right? That's the angular velocity. That is the initial angular velocity equals 0 radians per second. It's not moving initially. It's at rest. Its angular velocity, all right, increases uniformly. So it increases at a constant rate. And it reaches omega final is equal to 80 radians per second after time t equals 5 seconds. The net angular displacement will be what? So what are they asking for? They're asking for the angular displacement. I'll copy our table down maybe so we can see it again. But that is theta that they're asking for, angular displacement. Let's see if we can get this back for our reference. So theta was the angular displacement, right? Maybe I should have added another column to this. Let me do it. We insert on the left. Okay. Okay. We can say this is displacement. This is velocity. This is acceleration. Add some labels there. Okay. So this is where we're asking where we're going to solve it. So we want to go to our kinematic equations. This is a problem of motion. You maybe have your kinematic equations memorized by now, or you probably have them handy. See if you can solve the problem from the information that I gave you. If not, then we'll give it a go. Okay, so we paste in our handy dandy kinematic equations. Let's get that on our sheet right underneath here. All right, now these are in the form for linear, but it's okay, we know our analogs. So we're looking for something that, based on information about the final and initial velocities and the time, we can deduce the change in or the total displacement. So let's take a look. I see we've got, this one's good, except for acceleration, we don't have, right? Acceleration, we don't have. We could maybe find acceleration. So this might be okay, but let's see if there's one that's even more direct. This one tells us XF, which is the displacement, right? If we know the initial displacement and also acceleration. So we don't have that. Let's see if there's anything more direct. This one also has A in it, right? Same problem. What about this one? This one tells us XF, if we know X naught, 1/2 VF, V naught, and T. So we do know everything in here. This one we're ready to just plug in and solve. And you might have already done this with a different one of these equations, and that's totally fine. You can get there. This is just probably the fastest way. So XF minus X naught, right, is delta X is equal to delta X. Our analog, if we want to translate this equation, we can use this table right over here. We have that becomes delta theta, the angular displacement. The angular displacement is equal to 1/2 omega F plus omega naught, or initial, I should say, which is just the average of the angular velocity times the time. Okay, and if we plug in numbers to this real quick, I don't even think we need a calculator. We've got, this was 80 radians per second. This was 0. 1/2 of 80 plus 0 is 40 radians per second, 40 rads per second, multiplied by 5 seconds. 40 times 5 is what? 200? 200. So answer is C. This is 5 seconds. We've got seconds and seconds cancel out, and we end up with 200 radians. So we turn 200 radians. That's our final answer. Cool, good solve. Let's take a look at the next one. Okay. If angular speed of a disk depends on angle rotated, theta, as the angular velocity is equal to the angular displacement squared plus 2 times the angular displacement, then the angular acceleration at angular, okay, theta is equal to 1 radian is what? Okay, all right. So what is this asking? What is this asking? They tell us that the angular velocity, omega, is equal to theta squared plus 2 theta. And then they're asking us, when theta is equal to 1, what is the acceleration? All right. So in order to do this, we need to remember that for both angular and linear quantities, there's a important relationship between the position, the velocity, and the acceleration. Namely, it's that the velocity is the derivative of the position function as a function of time, and the acceleration is the derivative of the velocity as a function of time. So what is that to say? That is to say that acceleration is equal to dv dt. How the instantaneous change in the velocity at a given moment in time, which is also equal to the second derivative of the position at some instant in time. And that's because the velocity is equal to the instantaneous change in the position at some instantaneous change in time, right? What is velocity? It's a change in position over a change in time. What is acceleration? It's a change in velocity over a change in time. So with that relationship, let's translate it over to the angular quantities, and let's see if we can solve this. So we're saying that omega is equal to theta squared. And really, theta is a function of t, right? This is 2 times theta, which is a function of t. All right. So we're going to take the derivative of this. We're going to say that dw dt is equal to 2 times theta times d theta dt. Just doing our derivative rules here. And then this is 2 d theta dt. All right. So what does that say then? If we change this, we just said that d omega dt is equal to the angular acceleration, right? Is equal to the angular acceleration. So here's alpha. Okay. Maybe I should have been more explicit about this, right? This is coming from the table again. We're using our analogs. I could have written this. I could have written this as alpha is equal to d omega dt. Now we're talking about the angular quantities, which is also the same as the second derivative of d theta dt. And omega is the change in the angular displacement, the change in the angular position, dt, d theta dt. All right, so there we are caught up. So d omega dt is alpha. Then 2 times theta times d theta dt is omega, theta omega, plus 2 omega is equal to alpha. All right. And they asked us to solve for alpha, right? So in order to do that, let's first find the value of omega, right? So we know what theta is. They told us that theta is 1. Theta equals 1. Or they want us to solve for this when theta is equal to 1 radian. And then we also had the function that omega as a function of theta is equal to theta squared plus 2 theta. So omega as a function of 1 radian is equal to 1 squared plus 2 times 1 is 2. That's equal to 3. So the value of omega is 3. The value of theta is 1 radian. Now let's calculate the value of alpha. So then alpha is equal to 2 times 1 times 3 plus 2 times 3 for a total of 6 plus 6 equals 12 radians per second squared. Perfect. So the answer is C. Answer C. Okay, a couple more. I think maybe we have time for 1 or 2 more. And then maybe I'll post up the last one so you guys can work on them without me. Let's try this next one. A particle is moving with a constant speed. Okay, constant speed. So we have to be very, all this text is a clue for us. Constant speed of 5 meters per second. In a circle of radius 2 meters, r is equal to 2 meters. The acceleration of the particle is, question, what is the acceleration? Okay, so they didn't give us a lot of information. Let's see what we can do with this. The particle is moving with a constant speed. So that's to say what? That's to say that the magnitude of the velocity, without regard for direction, the magnitude of the velocity is 5 meters per second. So we may be changing direction. In fact, certainly we are changing direction because we're traveling a circle. but we're traveling at a constant speed of 5 meters per second nonetheless. Now we have a radius of 2 meters. R is equal to 2 meters. Okay, so those are the 2 bits of information that they gave us. And they say the acceleration of the particle is what? They say the acceleration of the particle is what? All right, so let's take a look at this particle. It experiences this velocity of 5 meters per second. And there must be some acceleration which is causing it to seek the center, But the particle, is it speeding up or is it slowing down at all? Is it speeding up or is it slowing down at all? No, it is not. It's a constant speed. So we don't have any acceleration that's going in this direction or in this direction. We only have this centripetal acceleration. Is that right? Let's see. A constant speed, radius of that. Okay. Right. So if that is the, yes. Yeah. So just confirming the logic, it's very easy to get confused, but we have a constant speed of, so we're not speeding up and we're not slowing down. So there's no acceleration present in a direction that's tangential to the circle. The only acceleration that's present is the one that changes the direction of our velocity and makes us travel a circle, the centripetal acceleration. And we remember, we had our equation for it up here. Let me go find it for us. Let's see if I can copy that. We remember what we know about the centripetal acceleration. It's equal to the square of the velocity divided by the radius, the square of the velocity divided by the radius, or it's equal to the radius times omega squared. Okay, now did they tell us the radius, did they tell us the angular velocity, or did they tell us the linear velocity? The linear velocity. Think about that for a second. They told us the linear velocity. I wrote it right here. They told us how far we're traveling in terms of meters per second, right? Not in terms of an angle. They didn't tell us how many radians are we turning per second. They didn't tell us how many degrees are you turning per second. They said how many meters are you traveling per second. They give us a velocity. Okay. This is actually really straightforward. We just have to plug in the pieces. The only difficult part, or the only trick to this is just making sure you know these arrows. So we've got 5 squared divided by 2 meters is 25 over 2 is equal to 12.5 meters per second squared. Okay. So all of these questions that we've done today are really straightforward. Like the math is super simple, and I didn't want to get bogged down in the weeds of anything. But what we do want to make sure that we understand the distinctions of are the groupings of these formulas and when to apply them and what specifically they mean. So if we do a brief review just before I jump off here, we're talking about a couple of different things. There's angular quantities. We're talking about circular motion. We need to consider these angular quantities. Sometimes when you get information about these circular problems, we know things about the period, we know things about the frequency, and we're thinking about how much of a circle do they turn for some given amount of time or something similar to that. And there's a relation to the linear quantities that you previously learned about, and it's related by the radius. So the displacement is the radius times the angular displacement. The velocity is the radius times the angular velocity. The acceleration is the radius times the linear acceleration. Now, we've got to keep straight our alpha, our acceleration A, and our centripetal acceleration AC, our centripetal acceleration AC. Each of these is different. Each of these is different. And I challenge you to explain them to me or explain them to yourself after we've gone over them. This is the big key, I think, to get these problems understood, to have an easy time with them, is to know the difference between these accelerations. Don't get confused with these different A's. It's a common pitfall. We've got our centripetal force. That's where our centripetal acceleration comes in. We did a couple of different problems. I'm going to post 2 more for you guys, 1 or 2 more. Pause the video and try those out yourself, and then I'll post the answers so you can reference them. So what do we have here? We have 5 and 6. The velocity of a body moving along a circle and a particle moving in a circular path with a speed of 1 meter per second. You can try those out. Give it a pause. See if you can solve those, and then I'm going to post you the answers. Okay. These are circular motion problems. And answers for 1, 2, 3, 4, 5, and 6 are here. Okay, so I hope you found this helpful. We'll review more in future workshops. And if you guys see me in person, then we can definitely go over working out these problems side by side, or visit the NatSci Tutoring Center, and you can get more work in depth with us. Thank you for tuning in today. I hope you have a great day. Signing off.